Let's talk about just a little bit about the probability laws for the intersection, or in other words, when two events are connected with an and to make a more complicated event, and a little bit about the concept of independence, which is the deepest concept really in probability. So just a couple of examples to get a little bit of these ideas. Let's say event A is that the first roll is at most 2. That's an event I used in previous video. And then B is that the second roll is at most, let's say, 3 to be just a little different. Okay, so let's draw those. And so let's say A was usually green for me. So the first roll that's the rows of this guy. That's most 2, and so that's the green there. And then the second roll is at most 3, so that's these 3 columns. Okay, and let me go ahead and calculate the probability of the intersection. That's just everything that is every outcome that simultaneously A is true for and B is true for. In other words, you can think of it as the probability of A happening and B happening. Very different from OR. So it's the overlap, not everything in both, which would be the union. Okay. Well, it's rather small. It's everything in this box here, this 2x3 box. That's the overlap of those guys. Okay. And that's going to be 6 over 36. Now, how does that correspond? How does that relate to probability of A itself and probability of B itself? Well, the probability of A, well, we could write it out as 12 over 36, but in this case, there's a nice way to reduce that. It's complete rows, and it's 2 rows out of the 6 rows, so that's 2 out of 6. The probability of B, similarly, we could write it down as 18 over 36, but it's a little bit silly because it's complete columns. It's 3 complete columns out of the 6 columns. Aha, notice that this is probability of A times probability of B. So at least in some cases, the probability of the conjunction, the and or the intersection, all these equivalent words, of 2 events is the product of those probabilities. Now, I just recorded a video about OR, where we noted that there was really an assumption that had to be satisfied for that to be true. Let me see if I can. I need to wet my little eraser thing. Let me erase the blue and the green there. It's a little messy, but that's okay. Actually use this part of it. Okay, so now I want to try another example. I'm going to leave A the same, and I'm going to change B. And we're going to see if that's always true, and it won't be. And then we're going to try to see what is true, what was special about the first example that made that work. So, dry erase marker. Let's say B, let's put a condition on the total, the sum. Let's say the sum is at most 7. Okay, so that's a familiar event from other videos. So, let's see, once again, the green is everything up here. Okay, that's A. And then the blue is the at most 7s. That's everything above this jaggy line, including the diagonal, all that stuff. Okay, so now let's calculate those 3 numbers and see what happens. Probability of A alone is still 1 out of 6. Oh, sorry, 2 out of 6. Probability of B alone, well, probably the best way to do this here, there's more sophisticated ways, but you can just count, and this is a pretty standard thing, it's 21 over 36. The probability of them both happening is, okay, we can just directly count that. That's the overlap. That came up in another video as well. It's all 6 of these guys and just the 5 here. Because this is in green, the first roll is 2 or less, but it's not, the sum is not less than or equal to 7. And then everything else doesn't satisfy the condition on the first roll. So it's 11 over 36, okay? And let's see, if I multiply these 2 guys together, probability of A times probability of B, That's equal to 42 over 6 times 36. Well, that does reduce a little bit. That's a 6 times 7, so that's 7 out of 36. It happens to reduce to something nice out of 36, but it's definitely not equal to 11 out of 36. Okay, so here the probability that both things happened was bigger than I might have expected if I thought the probability of A times probability of B calculation was always correct. Okay, what's going on here is it's nice to think about this in terms of areas. Okay, in the previous example, oh, I shouldn't have actually erased it, but I can bring it back. In the previous example, there was a nice pattern in terms of the areas here. This was half of the area of the square. This was a third of the area of the square, and the same is true when I look at the overlap, that the green and blue was a third of the area of the blue, just like the green is a third of the area of the whole square. So the proportions are the same. Similarly, the area of the green and blue is half the area of the green. That's just like the area of the blue is half the area of the whole thing. When you have that proportionality, that's when you get that the area, the number of boxes here, of the intersection is just the product of the area of the green and the area of the blue. The probabilities multiply. And this picture where you have their kind of nice perpendicular rectangles, that's the kind of picture that you really want to think of as a Venn diagram corresponding to independence. It really matters the sizes of these things. For other Venn diagram pictures, you don't usually, you just have the circles or random blobs or something like that. Here it really matters. What's happening in this example is that overlap is bigger than expected. One way to think about it is that if I know that the first roll is at most 2, so I've got a small first roll, if I want this outcome, that the sum is at most 7, that's good news, right? I would not like to see the first roll be a 6, because then I'd have to get 6, 1, okay? But if the first roll is at most 2, then there's very little way that the B could actually be false. Because if the first roll is most 2, I'm in the first 2 rows, there's only one way. I could have to get really unlucky for B to be false. Okay, so that perspective of looking at one event and how it affects the other event leads us to the other thing. It's always related to questions of intersections and ands and independence. That's the probability of B given A. That's a conditional probability. Okay, and what that is you look at the sample space that's just the event A. It's a new sample space. That's the green. Out of those 12 possibilities, what you imagine is you've done A and you're sure it's true. And then you look at what's the probability that B will also be true. Okay, well, that's going to be those 11. That's very, very high. Okay, and what that is, another way to say it, is you take the probability of A intersect B, you look at the overlap as a proportion of the area of A, and that's really corresponding to the probability of A. That's just the same thing with the denominators put back in. A intersect B is 11 over 36, and this was 12 over 36. They just cancel down to 11 over 12. So usually you'll see the conditional probability defined this way, that it's a probability of both the things happening divided by the probability that A is true. But that is a little misleading because it suggests you have to know these two and always calculate this way. A lot of the times you actually know this first and it helps you calculate, say, the probability of both things being true. In this case, at the very least, we can say that the probability of B given A, if you tell me that I just rolled the first roll of 2, I can at least say, oh, that's greater than just the probability of B if I didn't know that A was true. Ooh, it's not really visible. Okay. This guy is quite big, 11 out of 12. If I know this is true, I'm pretty sure that B is going to be true, unless I'm really unlucky. Whereas the probability of B was only a bit over a half if I didn't know that information. Okay, so this is a really good picture to go back to for these key concepts of and intersection and conditional probability. So the upshot is that in that second example, we did not have independence. So if you have independence, and that was this picture with the rectangles kind of intersecting nicely perpendicularly, okay? If independent, then there's three ways to phrase that. The probability of both being true is the probability of A times the probability of B. You get it, multiplication law. Another way to say it is the probability of A given B is the same thing as the probability of A. And the probability of B given A, telling me that A happened makes no difference because these guys are independent. Whether A happens or not doesn't affect it. Okay. So for example, here, this guy, the probability of A was the green. That was 1 out of 3. That's the same as, and this is what I was talking about, the proportions. The probability of A given B is again, oops, wrong case. The probability of A given B is out of the blue. That is, I'm just going to assume that B is true. Out of that, how much is green and blue? It's 1/3. And again, that's the same as the proportion of the green out of the total. It's exactly a conditional probability kind of statement. And similarly, the probability of B given A, that is, assume A is true, so assume you're in the green. Look at the probability that that B is also true, and that's 1/2. Just the blue is the blue and green is a half of the green, just like the blue is a half of the total. That's the blue and green as a proportion of the green. That's the blue as a proportion of the total. In this special kind of geometric situation, where the pictures are so pretty, those are equal. And we already verified that this was true. Okay. If not, and that's this picture. If not independent, then P, probability of A and B both happening, will never be this. It's by definition. The probability of A given B, the conditional probability, will not be the same as probability of A. Saying that it's not independent says that knowing B has happened will affect the probability of A, and it's symmetrical. That it says knowing A is true will affect the probability of B. And there's more to say about this, certainly, but that's a good start and a long enough video.